So is it readable from other side?
Okay, so we can do that.
Good afternoon, everyone. So I'm very pleased to introduce the speaker of our seminar today, Dr. Arindam Roy from University of North Carolina at Charlotte, one of my very good friends and collaborators from PhD days. So Arindam did his PhD from University of Illinois at Urbana-Champaign, followed by a postdoc at Rice University, and then he joined University of North Carolina at Charlotte. I was there with him on his first day of joining UNC Charlotte. So, Arindam today will be talking on the hyperbolicity of Ensign polynomials for power partitions. Over to you, Arindam.
Thank you, Atul, giving me the chance to talk in this seminar, and thank both Atul and Gaurav for inviting me. I'm going to talk on the hyperbolicity of Ensign polynomials for power partitions, and this is a work with one of my students. And let me get to the talk and try to see the backgrounds and why this work is interesting. I'll try to explain. Before I go to the details on the partition side, let me talk a little bit about the Ensign polynomial. And recently, some of you may follow that is kind of a interesting paper by Ono, Zagie, Griffin, and Larry Rowland. So if you take any arithmetic function, a real valued arithmetic function, or we can think FNR sequence, then the Ensign polynomial of degree D and a word shift n defined by m0 to d choose m, f of m plus n, so the shift n, x to the power m. So so this is just a polynomial where the coefficients are this binomial coefficient and with the sequence with the shift. And actually easy to see that if you take n equal to 0, then the Ensign polynomial of degree D shift n is nothing but the nth derivative of the Ensign polynomial degree D with no shift. So this is just a definition of Ensign polynomial. Now let me tell you what do you mean by the hyperbolicity of Ensign polynomial. So a polynomial is said to be hyperbolic if all its roots, all the zeros, are real. Now, if we consider a real entire function psi x, and let's consider the Taylor expansion of psi x is summation nu kx to the power k over k factorial, then we'll call this entire function psi x is in logger polya class, or let me do in short LP class, if psi x has look like a Hadamard product, if we think it is an entire function, or psi x is written as some constant c times x to the power m times e to the power minus alpha x square plus beta x times this infinite product with the sequence xk satisfy this convergence condition. Now, what to do with this hyperbolicity of a Ensign polynomial and what to do with this logger polya class? Now, it is in 1912, so in 1913, Ensign himself saw that if you take a real entire function psi x, then it is in LP class if and only if the Ensign polynomial of degree 0 are hyperbolic for all degree D. So in other words, we just from now on, if we just take we understand the meaning of psi x is in LP, mean this corresponding Ensign polynomial is hyperbolic. There is another result. It is by not this result. I didn't write it down. It is by to another same polya. And the Shure is, I think, a famous name among combinatorics. They saw that if let me remember, yes, I think if this is an hyperbolic, then I think you can take the derivatives and they're also hyperbolic, if I recall the results. So sometimes people do mention that if psi x is in LP, that is also give you that any derivative of sin x is also in LP, because when you take the derivative, the corresponding Ensign polynomial will be just the shift. But anyway, I think the most interesting thing that motivated study further was the result by Polya, and he saw that Riemann hypothesis is equivalent to the hyperbolicity of all Ensign polynomial. Now I put a star here. I'm going to tell you why it is star. Ensign polynomial of the completed Riemann zeta function. Now the star will be the sequence coming from the Taylor expansion of this completed Riemann zeta function, and not directly to the Taylor expansion of the completed Riemann zeta function. You need to do some normalization. And I think I did not include a slide about the Riemann zeta function, but I'm going to quickly just give a definition of the Riemann zeta function, what is the Riemann hypothesis is. So the normally whenever we write Riemann zeta function for a complex variable s, we understood by this infinite series 1 over n to the power s. Is it readable or too small?
No, it is readable.
Okay. For when you take these complex numbers, live in the plane real is greater than 1. And also there is an interesting fact. It is connected to this prime number by this relation. And there are another fact is the completed Riemann zeta function is given by this adjustment of the Riemann zeta function multiplying by these factors. The reason is, if we draw the complex plane, let's say this is, if you take S to be sigma plus IT, this is the sigma, this is the T line, and let me put another line here, that is, let's say sigma equal to 1, and let me draw another line right here, sigma equal to 1/2. Then this is telling that Riemann zeta function is defined in this half plane, and the reason of multiplying these factors, this allow someone to continue Riemann zeta function analytically beyond this line, so going here. So then kind of we will understand that Riemann zeta function is defined by this side, and then there is a lot of study going on. For example, if we take the negative integers, even integers, then it's turned out to be these numbers are the zeros of the Riemann zeta functions. And not only that, there are a lot of numbers on this line they're the zeros of the Riemann zeta function. And there is a famous conjecture, which is called the Riemann hypothesis I just mentioned on the last slide, is assuming that all the zeros other than these zeros should lie on this line. So this is an open problem. And because it's really difficult to solve, people always try to find an equivalent condition to this Riemann hypothesis and try to work on other. And one of the equivalent condition was by Polya, just I mentioned that Riemann hypothesis is equivalent to the hyperbolicity of all Ensign polynomial. And the reason is it is really appealing because we are looking, so Riemann, if we see the Riemann hypothesis, we are looking the zeros of an infinite series kind of wrong way. Actually, you're looking zeros of this function, which is a complex function, not easy to handle. On the other side, if you look at the Ensign polynomials, they are polynomials, but then there is a bad side is because you have to look for all degree d and all n. But still, people thought it is more appealing. And so very recently, so excuse me if I miss any result from Polya to Griffin, Ono, Roll, and Zagier, but I think the kind of a major advancement made by Griffin, Ono, Roll, and Zagier, they actually first studied the Ensign polynomial for the completed Riemann zeta function, and then the same paper they did actually study Ensign polynomial for a large class of function, because it is just a natural question that if Ensign polynomial for the completed Riemann zeta function is equivalent to the Riemann hypothesis, of course people can ask what is the questions for the other L functions. There are Riemann hypotheses and still open problem. So basically, is it worthy to look the Ensign polynomial corresponding to those L functions or so on? So that's naturally the question is, natural question was to study the Ensign polynomial for a large class of functions. And in this, please stop me if anyone has any questions. And so in this paper, they showed that, they showed that eventually all the Ensign polynomial corresponding to the Riemann psi function or completed Riemann zeta function are hyperbolic. So that being said, it is a very strong result, but we are still very far from proving the Riemann hypothesis, because to prove the Riemann hypothesis, we literally need the hyperbolicity of each polynomial of each degree for all n. So there are some controversy, people, some mathematicians feel that maybe using the hyperbolicity condition to attack Riemann hypothesis is not viable, is not the right path. But nevertheless, that problem itself is very interesting. So in the same paper, they did not only look the Ensign polynomial for the Riemann psi function, a completed Riemann function, they do also look a big class of function, including partition functions and Fourier coefficient for the weakly holomorphic form. Now, there's kind of like this is the background part of the hyperbolicity and Ensign polynomial and some recent study. But from now on, kind of we try to focus our study on the partition functions and similar functions and corresponding study of the corresponding study towards the hyperbolicity. So any questions so far? Okay, so next we'll talk about partitions, and I'm pretty sure there are experts in the audience who are who know way better than I about those things. So the definition of the partition is the way of representing n as sum of positive integers, where integers the integers. So you want to see how you can write n as a sum of lambda 1, lambda 2, lambda k, with the fact that they are monotonically increasing. None of them is 0, and each of lambdas called the parts of that particular partition, and number of way of writing that is the number of partition of n. And this is a very old problem, and like we already start seeing movie, Hollywood movie, and also in Bollywood movie on that this kind of problems. One example is like and this is a probably classical example people take in the area of partition, that you start looking the partition of 4, which is written as 4, 1 plus 3, 1, 1, 1 plus 1 plus 2, 1 plus 1 plus 1 plus 1, 2 plus 2. So basically, how many partition you have? Total number is 5. Now, the mainstream of study of partition is, I believe, looking various arithmetic property, and whenever I say various arithmetic properties, kind of focus in one part, looking congruences. So if you think the partition is a sequence, are they satisfying any congruence relation, and so on and so on. But there are another side of study, and this is less observed, is looking some analytic property of the partition function. So one of the analytic property is, let me first look the Ensign polynomial for the partition function. So basically, we're representing we consider the same polynomial, but the coefficient will be now a partition function. And this is a Ensign polynomial with shift n. And the more analytic study is try to understand. There are many. Actually, I'm not going to focus all of them, but in this talk, we're going to focus the hyperbolicity of this. Ensign polynomial. So, so when I was looking this problem, sorry, should I answer the question now, or?
Yeah, you may.
Okay. So, do they satisfy the binomial conditions? Could you elaborate what do you mean by binomial conditions?
Professor Ajit? Yeah, if you could elaborate on the...
Yes, like Pn at x plus y is equal to NCR, x raised to r, y raised to n minus r, sum of that.
Oh, similar
That
like
is
that.
a binomial, binomial condition.
So I think you mean this coefficient or this coefficient? So
No, you see, you take the sequence of polynomial. Now take Pm at x plus y. That should be sigma of MCR, x raised to r, y raised to m minus r. That is the binomial theorem for the new polynomial. Binomial theorem is for the usual polynomial x raised to n.
okay.
And most orthogonal polynomials satisfy the binomial condition, like Chebyshev, Jacobi, they satisfy binomial condition.
That's a good question. I don't know actually, honestly, the answer is.
So I think Ken Ono and Christine Bessenroth, they have this inequalities for P of A plus B connecting P of A and P of B, but I don't think the binomial condition like that holds. Yeah.
Except A plus B equal to A.
Right. Yeah.
So yeah, I think, thank you, Atul. I think that for answering that. Yeah. So besides, I don't know a lot of relation, but but also it is not ring the bell that any other binomial condition satisfied there. I don't know, it's satisfying answer, but yeah. So, okay, I'll continue. Yeah, please. Oh, okay. So if you define the Ensign polynomial, so the question was what does the hyperbolicity? What do you know about the hyperbolicity of the Ensign polynomial? Actually, that I find out yesterday. So I always think this kind of question was raised by a numerical study by W.C. Chen, but it's turned out to be there's a much before there was a similar study done by Nicholas. It's 1978. So I really kind of now confused me when the study started. So the first result that I knew, but now found out there is another result by, I think, Nicole. Sorry if I misspell. I think it is much before 1978, around that. So the first study was done by Disselfan, Igor Pack. They said that if you take D to be 2, so if you take the degree 2 polynomial, Ensign polynomial, then this is a hyperbolic for all n bigger than 25. Now, when you look at the degree 2 polynomial, this is actually a quadratic polynomial. So you are looking, all the roots are real. That means you are looking the discriminant is positive, right? So that means the relation turned out to be that Pn square minus Pn minus 1 times Pn plus 1 is bigger than 0 for all n greater than 25. This also called log concave sequence, or the sequence Pn satisfy is log concave. So this is another word. The partition function is log concave. And also they call also the same thing if some partition function has satisfied two run inequalities for n bigger than 25. One thing I want to mention, before Disselfo and Pack proving that, I think it was conjecture around same time by W.C. Chen, looking at the numerical, and I think they did prove this is true for large n, and they did conjecture that for all n bigger than 25, it is hyperbolic. And I want to mention one thing. So, like normally, and I'll mention later on in my talk that getting hyperbolicity for large n kind of sometimes it is computable, but going down to the optimal value of this constant, in this case 25, is sometimes need laborious numerical computation or need some more hard work in the proof. Now let's see what is the next improvement. Then in 2019, Chen, Jian, Wang, they proved that if you take the degree 3 Ensign polynomial for partitions, then it is hyperbolic for all n bigger than 95. And that's also that is also like towards a next step to proving the hyperbolicity for Ensign polynomial for the partition function. So in more particular, what they prove that if you take un to be this sequence, Pn plus 1, Pn minus 1 over P square n, then for all n bigger than 95, this inequality holds. So this is precisely the discriminant for a degree 3 polynomial. And if you're looking this discriminant is positive, then you're telling this all the degree 3 polynomial has a real root. And then they went on and conjecture that for any given d, there will be a integer nd computable effectively such that the Ensign polynomial of degree d is hyperbolic for all n bigger than nd. This was the conjecture. And then there was a result which is parallelly going on, Larson and Wagner, and also Griffin, Ono, Roland, and Zaghi. At the same time, they're they were working. So that they use a little bit different technique, and the meaning of the different technique, the proof of this result and this result, the diself-opaque and change and Wang, they did use the asymptotic of the partition function, but Larson, Wagner, and Ken Ono, Zagier, Griffin, and Rowland, they use a different technique. What they did, they connect the Ensign polynomial for the partition to the Hermite polynomial. And what is the Hermite polynomial? You can think it is just a coefficient of some exponential. So I'm not going to go in details. They connect with these Hermite polynomials, and then they just look the roots of these Hermite polynomials, which is easier to study than the Ensign polynomial. So the technique for Larson and Wagner and other people, they're same, but what Larson and Wagner, they fine-tune the technique, and they managed to prove very accurately that if you take the degree 4 Ensign polynomial, then it is a hyperbolic for n bigger than 206, which is optimal. So basically, if you go 204, it is not going to work. And for degree 5 also, they said it is also hyperbolic for n bigger than 381. But from degree 6, they could not manage to compute, but they say it is a hyperbolic for some nd, and they give an upper bound of nd. They said that nd will be at most this number, 3d times 3d to the power 24d times 50d to the power 3d squared. And then Griffin, Ono, Rowland, and Zagier, on the paper I just mentioned previously, they said for each fixed d, there exists capital N such that the Ensign polynomial hyperbolic for all d bigger than n. So that, and then they give some numerical evidence for certain d, and the way they give that, it was not, if I understood correct, it is not exact, it is more like an approximate value of those d's and n. So that kind of telling that eventually all the Ensign polynomial of degree d for the partition function are hyperbolic. And then I want to mention that when you go to the partition, they also consider, and it's kind of work same way, they considered the coefficient for a holomorphic, weakly holomorphic forms, and they consider the corresponding. So basically, you consider the Ensign polynomial whose coefficients are AFN, and then they also managed to show that the corresponding Ensign polynomial for any degree and any n eventually hyperbolic. All right. Any questions so far? Let me move on to the next one then. Now I'm going to talk about another partition. It is a overpartition. And the definition of the overpartition is, again, it has to be number of partitions, sum of non-increasing, but what happening, it is not only the normal partition. Every time there is you see a first occurrence of the parts, you overlined it. So in this example, if I take it, if you look at the partition of 3, then it is 3, but then 3 appears first time, so I mark it. Then also another partition of 3 is 2 plus 1. Now the parts 2 appears, we mark it. Also the part 1 appear first time, we mark it. But also 2 and 1 both appear first time, we mark both. And then another one is 1 plus 1, but there's only one part here, and we just mark it. So it's turned out to be the overpartition of 3 is 8. And then next consider the Ensign polynomial for this overpartition. And then the question is same. What do you know about the hyperbolicity of this Ensign polynomial for any degree d? And what is the corresponding n? Like, is that hyperbolic for all n, or maybe there exists a number capital N from there on? Now, not long before ago, Angel in 2017, he first proved that the overpartition degree 2 Ensign polynomial for the overpartition is hyperbolic for all n bigger than 2. So it is behave better than the partition function. So in other words, they managed to prove that this relation P over line n square minus P over line n minus 1 time n plus 1 is positive, or in other words, this sequence is log concave. And then just last year, Liu and Zhang, they proved that if you look the corresponding degree T Ensign polynomial, this is also hyperbolic for n bigger than equal to 16. And again, UN is the corresponding. So here UN is just P bar n minus 1, P bar n plus 1 over P bar square n. After that, I don't see any study on that for all degree or things. Now, another result I want to mention, also related to that study in this area, is Andrew's smallest part function. And what is the Andrew's smallest part function? Is you take the partition of all partition of given integer n, but here you're going to count the smallest part on each partition. So you count total number of smallest part in each partition. So here one example is if you take a look, if you take 4, then the partition of 4 are 4, 1 plus 3, 1 plus 1 plus 2, 1 plus 1 plus 1 plus 1, 2 plus 2. But in partition, this one, the smallest part is 4, here smallest part is 1, and so on. So it's turned out to be SPT4 is 10. And then again, the same question, if you consider the Ensign polynomial for this smallest part partition, are they all hyperbolic? And there are, I was looking literature, and I think there is only one paper I find so far. This is a work by Madeline Dossi and Riyad Mashri. They show that they take the degree 2 Ensign polynomial for SPTN, and they say it is hyperbolic for n bigger than 36. And in other words, SPT n square minus SPTN minus 1, SPTN plus 1 greater than 0 for all n greater than 36. Now, there are, I just mentioned this 3 partition, the partition function, the overpartition, and the SPTN, and the smallest part function. There are some study on some other partition function. I just don't want to mention all of them, but I want to mention that this 3 partition has some arithmetic structures. So what one way to look that all those 3 partitions satisfy certain kind of congruence relation, and normally they are somehow embedded back to their structure, so that satisfies some kind of their generating function, satisfies some kind of modular transformation. But the question is here, sorry, before we ask the question, so there are some other results, for example, like Craig and Poon, they actually look the K regular partitions. So K regular partition, you look the parts which is divisible by K, and then they look this, I think, able to show that for the corresponding degree 2 Ensign polynomial for K regular partition is hyperbolic. I'm not sure any study for degree 3 is there. And then very recent, there is a paper by Brinkman, Kane, Rollin, Ben Ken, Rollin, and Zach Tripp. They look the generating function for partition function, which is with some adjustment, it will give you some modular form. Then you take like a kth power of that generating function. So the corresponding coefficient will be fractional power of the partition function. And they look the, they consider the corresponding Ensign polynomial. And mostly they look the degree 2 and degree 3, I think. And they study the hyperbolicity of that. So the question is, if we take a general partition, so we take any subset, we take A is any subset of N, and we consider the partitions where the parts coming from that set A. And then you can take any arbitrary subset, and then you could consider the corresponding, let's start with the easy case, the degree 2 Ensign polynomial. The question is, are there hyperbolic? So remember that for any A, there are some A's, subset A, PA kind of lose some structure. So this general question, but the question will be more interesting. What kind of A will give you the hyperbolicity of degree 2 and degree 2 Ensign polynomial? So in other words, for what kind of subset of what kind of set A, we are looking this fact that PA square minus PAN minus 1 times PAN plus 1 is positive. Oh, sorry, I already wrote it. And then big question is that hyperbolic for all degree D? So we started looking these things. We started working on, we could not able to take any A. We just, okay, let's start with A, which is the content all the kth power. Now, one can ask that why just choose why A content only kth power, not the other things. Now, there is some interesting fact. If you choose A content all kth power, that means you're looking the partition Pn, while A are the just a kth power. So this is different than the previous three partition I gave you in the example, that is the partition of N, over partition of N, and SPTN. And again, correct me if I'm wrong, as I say, there are, let's say there are congruence relation known for these three partitions, but I think there are no congruence relation known for this Pn, where A is the just kth power set. So in other words, not other words, so also like if we go back to the generating function of these three functions, as their generating function has certain kind of modular transformation, the generating function for this one do not have any modular transformation. So that is the basic difference. So we are looking a set where we are losing that structure, and we try to see what's going to happen. So of course, the first okay, before I go to the numerical, which is the big help, let me define what is the power partition is. So power partition is basically N can be the number of ways you can write N as a sum of kth power. So for example, if you take 4, you can, there is two ways, 4 and 1 plus 1 plus 1. If you take 5, again, there are only two ways, 1 plus 4, 1 plus 1 plus 1 plus 1 plus 1. If you take 6, again, there are two ways. I think 7 2 ways too. But when you go to the 8, then you can see it can be written in 3 ways, like 1 plus 1 plus 1 plus 1 plus 4, 4 plus 4, and 1 plus 1 plus sum of all ones. And the reason I wrote a little bit more, one interesting thing one should notice that if you look the partition function A, just standard partition function of an integer N, it is strictly increasing. That means Pn plus 1 is strictly greater than Pn. But the case of power partition, at least for k equal to 2, you can see that it's not a strictly increasing function. So it is like a sometimes stay same number, then go up, and so on and so on. And then we're gonna look the Ensign polynomial for this pkn. Most of the numerical study we did for k equal to 2 and k equal to 3, because when k become bigger and bigger, generating all the pkn is really a time consuming. So let me show you the first numerical result. So we look the degree 2 Ensign polynomial for P2. So you try to write integer n as a sum of square. And then we just consider this function p2n square minus p2n minus 1, p2n plus 1, and you just draw that graph. And it started to be really nice. Then initially it was a little bit oscillated, and then from some point close to 1000, it is just nicely increasing and look like a going to the infinity super fast. So that point we start feeling, okay, it is then log concave, or this polynomial is hyperbolic. And then we also did study for we take degree 2, but we study for the parts the cube, third power, fourth power, fifth power, and so on. So next we can see that. So we are studying. So there are like all the graph for different power. I think the first one is for writing n as a sum of cube. Sorry, not sum of the cubes. Yeah, sum of cubes. Yes. So you look this difference, and we draw that. And again, it was oscillated in at the beginning. Then the sum point is really going to the infinity. So I think that's what numerical studies clearly giving us that both degree 2 for, I think like we kind of went on until not, you can replace 2 by k, and you can take basically any power partition. And if you look the degree 2, or you can say the power partition is log concave after a certain point of view. And I think we did briefly look the degree 3 polynomial, and I think we had also hyperbolicity for the degree 3 polynomial, but we did not prove it. It is a numerical result, but we tried to actually prove this kind of result for power partition. So first we make some conjectures, and they're still open. So the first conjecture is, if you look this particular graph, which is, we're considering the degree 2 polynomial, whose coefficients are the p2n, writing n as sum of square. And if you notice carefully right here, the number is close to 1000. And we've managed to precisely, more by just zooming in, we managed to find out that if you take any integer n bigger than 1042, then the power partition p2n is a log concave, or in other words, that jp2n is hyperbolic. And then we also did for the degree 2 polynomial for p3n, and we also find out numerically that as long as you take n bigger than 15,700, then this polynomial is hyperbolic, or p3 is log concave. And actually we did manage to find out a bunch of other numbers. I just don't want to write all of them. It's just, you see, for the numerical, you just take time and you can start getting all those things conjecture. And I think the big question is that big conjecture should be, there exists an integer n which is depend on the degree d and the power k, so that this Ensign polynomial jpk dn is hyperbolic for all n bigger than ndk. And for a fixed k, let's say for 2, getting the nd will be challenging. First thing is proving, like I'll tell you why, just if you look this conjecture, why proving, I'll try to explain why proving n greater than 1042 will be challenging. So in general, if we take any degree, it will be much more challenging to get this ndk. All right, so, but we managed to prove, we cannot prove this things hyperbolic for all n bigger than 1042, but we managed to prove that. This is the result with my student Winfield, Paul, and myself, that for a fixed positive integer k, so you take the k fixed at a time, then there exists an integer nk depending on the k, which is k is the power, such that the degree 2 Ensign polynomial jpk2nx is hyperbolic for all n bigger than nk. Note that if you take k equal to 2, we still could not manage to find what is the int. We just said there exists. The conjecture is saying it should be 1042. So it should be 1042. So proving for k equal to 2, n2 equal to 1042 is still conjecture. And we also numerically we have that if we do the degree 3, I think we are working on that. I think we'll also able to, I don't want to say it is a theorem now, but I think we'll still able to prove that for degree 3, it is also hyperbolic. Okay. How much time I have? Can I get a 5 minutes maybe?
Yeah, of course. I think you have 12 minutes or so.
Okay, yeah. So I want to don't want to go to the details on the proof, but now I want to a little bit discuss what is the reason to so just let me convince you. So basically you see that there's a two part. One, proving something is hyperbolic for large enough n, as I was mentioning before, and another result is proving this hyperbolic for small n, right? There's a two part, and most of the result for partition function n or the SPTN or the overpartition, you see that the proving hyperbolic, at least let's say degree 2 polynomial, for n bigger than a precise number like a 25 or 95 or 16, something very precise number. And our result is telling that, okay, there is a large n, this is happening. So going down to the small number, and I'm going to tell why this is challenging and why they get success for the partition function or overpartition or SPTN, and what is the roadblock for the power partition. So the first important thing we need to notice that these three function Pn, Py, and SPTN, and of course that is a similar other function, they have a very nice, very fine asymptotic. Now, what do you mean by fine asymptotic? What do I mean by that? So asymptotic, first for the partition function Pn, that famous Hari Ramanujan first they proved that this partition function Pn was asymptotic to 1/4√3n times e to the power pi square root of 2n/3. So again, this asymptotic is really good, but to compute this kind of hyperbolicity is not enough. So what we need the asymptotic which is obtained by the Rademacher. And Rademacher actually recycle the same method, the circle method by Hari Ramanujan. Only the difference is he chose the path of the circle, or basically he chose the arc. So normally whenever the circle method comes, there are two terminology appear, is called minor arc and major arc. So the arc Rademacher chose is very clever, very genius, I will say, and that allow him to get a very accurate asymptotic. And you can see it is not only accurate, you can make it accurate as much you want, because it is just a representation as an infinite series, where this coefficient SCN are some kind of Kusteman sum of the form e to the power pi I time a function SDC time e to the power minus 2 pi I dn/c, and this SDC is the I think Dedekind's sum, and there is a Bessel function. And I think for first few, I mean, these ACNs are pretty much computable, not that bad. So this partition function has this representation has one beauty is, I mean, just a little bit work, one can write that partition function has a, let's say, a main term and error term. Let's not focus on the error term because of course it's smaller than main term. But if you notice the main term, it is look like a root 2 square root of 12 over 24 n minus 1 time 1 minus 1 over mu e to the power mu, and the most importantly next term minus 1 to the power n over root 2 e to the power mu over 2. So, and mu is given by that. So my point is, if you let's say if you factor out e to the power mu, then the first term look like a 1 over 1 minus mu, but the second term e to the power minus mu over 2. So my point is that the second term all of a sudden has an exponential decay, and that was the key factor to get the hyperbolicity for the partition function, that like you really like working with just the first term, because the second function, we don't have to go Rn. The second term in the main terms, the secondary terms, is enough to get that n greater than 25 in the DCL1 packed result. So this kind of asymptotic is not only the partition function. Normally it is depend on the generating function of the partition function, and basically they satisfy certain modular transformation. Actually, they come from modular form, and one can allow that kind of modular form that they all satisfy this kind of. So there are like there are some arithmetic behind the scene helping to getting this type of asymptotic for these functions. Now, similarly for the SPTN, it was defined by George Andrews, but Catherine Brinkman first find an asymptotic that, okay, SPTN, and using the same circle method, SPTN is asymptotic to root 6 over pi square root of n time Pn. Although like a SPTM is not quite nice as a Pn in the arithmetic nature, but still there are some transformation involved, and that enough to give them the asymptotic. And later on, Algren and Anderson, I don't know if Atul was that time there or you graduated when they presented the paper.
I think, yeah, I had just graduated. So it was around 2013.
Right, same time. So they proved the Rodemaker type asymptotic for SPTN, and they did use circle method, but they have to use a different technique in the theory of modular form, and they get this kind of result. The Heresian is the same Kusterman sum, and then they have this different of the Bessel function. And one thing notice, in the case of partition function, the series was I would say both series are convergent, but this series convergent much slower than the counterpart of the Pn. So it was really good, but not yet really effective to get the at least the log concavity for the SPTN. So Doisy and Riyad Masri, they managed to fine tune their result, and they get another asymptotic, I mean same asymptotic with more better error terms, and they get the log concavity for the SPTN, or that mean hyperbolicity of degree 2 things. And similarly, if you look the overpartition, again for the overpartition, it was studied long back, and Hardy Ramanujan themselves give a asymptotic look like 1 over 4 pi, then derivative of, so this is a derivative ddn of this function e to the power pi root n over root n, and so on. But later on, I mean, this is not enough for the study of the hyperbolicity, but later on Zuckerman give more precise asymptotic like a Rodemaker type. And what I mean whenever I say Rodemaker type, you have a very fine-tuned error terms, and that allow to study the hyperbolicity of degree 2 and degree 3 Ensign polynomial for overpartitions. Now, all these three cases, I tell Pn, SPTN, and overpartition Pn, their generating function satisfies some modular transformation, and that's really important to get this kind of nice asymptotic. But when you look the power partition, when you go to the power partition, sorry, I just mentioned that power partition, this thing fell. So actually, again, thanks to Hardy and Ramanujan, for the power partition also, they did get a asymptotic for the power partition. And the asymptotic was not that good as the case of partition, but they said that, okay, if you take the logarithmic, log pkn is asymptotic to k plus 1, 1 over k gamma 1 plus 1 over k, zeta 1 over 1 plus 1 over k to the power k over k plus 1 times that. Okay, so let me go quick actually. So in particular, if you look P2n, then P2n look like some constant 1 over 2 pi times 1 over n to the power 3 over 2. Then you take a Bessel function whose argument is root n with some constant plus big of e to the power alpha n over 1/3. Okay, I mean, in this particular partition, it is given by Wright. It look like kind of a Rademacher type, but it's not that effective. I'm going to tell you in the next slide that. Let me look this method actually. Sorry, I'm going little hard. So what is that? Like this result by Vaughan. Vaughan did the same result as Wright. The only difficulty is Wright's method was more complicated. Vaughan used the circle method and it's easy to see the heuristic. And Vaughan proved that if you take capital X and capital Y, they're connected by this kind of equation. So basically, you can think capital X some kind of function of n, capital Y is some kind of function of n, then P to n is asymptotic to e to the power 3/4 zeta 3 half times square root of pi x minus half over 4 pi to the power 3 over 2 y to the power half. And then the important thing is noticeable. Then you have 1 plus k equal to 1 to capital K ck over capital Y, and capital Y, let's say, look like a root n. So basically y to the power k over 2 plus big of y to the power minus k plus 1 over 2. So my point is here, as I was mentioning in the case of partition function, let's go back quickly. Sorry. Yeah, right here. So you see that when I was writing here, if you factor out e to the power mu, the first term is constant, second term immediately give a exponential decay. But if you look the result in the Vaughan right here, first term is constant, second are the next terms are polynomial decay. And that was the main roadblock to get the hyperbolicity for the power partition. So the way we managed to did that, we actually what you have to do in order to compensate the exponential decay, we take a large value of capital K. So we get a polynomial decay in each term, but some point we enough polynomial decay to do the job. But then there is a compromise you have to make, because we have to then know what is the constant C1, C2, Ck to get the result that n greater than 1042. Now, in practice, this, like in theory, they are just a real constant, but in practice, the computing them need a really heavy computation because they are solution of some system of linear equation, probably of maybe 200 variables, something like that. So that's why getting the conjecture done is a lot of work, but at least if we know this is a real constant and take a long enough polynomial, we can get a capital N. So the n greater than capital N, P2n, and not only P2n, for any pkn, you can get the hyperbolicity for the degree 2. And also, I think we'll be able to get the degree 3 Ensign polynomial. And lastly, I just want to mention that actually in the proof, you just need that good asymptotic and a simple result from the calculus that if you take a f which is look like completely monotonic function, and if that one can prove this relation that f double prime x minus 1 is less than fx plus 1 minus 2fx plus fx minus 1, and also it is bounded by f double prime x plus 1, that in elementary calculus result and the asymptotic result and some carefully applying the asymptotic result in this result will give the almost all the hyperbolicity result. All right, sorry, I have to rush a little bit. I'll stop here right now. Thank you.
Thank you, Arindam, for the nice talk. Are there any questions?
Hi. So may I ask a question?
Sure, please, Mithun.
Yeah. So thank you for this nice talk. So I just want to curious about the things that how the zeros are distributed on the real lines actually of this Jensen's polynomial.
One more time, go ahead.
How zeros of these Jensen's polynomial are distributed on the real line actually? Is there any result this kind of?
So if you look the polynomial, right, there are just finitely many roots, right?
Yes, exactly.
Yes.
But,
So
I
so
just
there are
want-
result I can tell the Ensign polynomial for the Riemann zeta function, not in general.
Okay,
So for the Riemann zeta function, that means not a Riemann zeta function, for the XZS function,
correct.
which is actually is a famous Polya conjecture. It was a Polya conjecture, and it was solved by Sordas. I think the Sordas spelling started with the C. They proved that. So if you look the Ensign polynomial for the complete Riemann zeta function, and if you allow to take the, remember the shift n, if
Yeah.
you allow to take n to be infinity, are you still there, or
Yes,
n
yes,
to
I am
infinity?
Yes.
Then the zeros of that Ensign polynomial is equally distributed. It's an equal spacing, excuse me, equal
Yeah,
spacing.
that's
The real
nice.
root,
Okay.
which is mean like look like the zeros of the cosine function.
Ah,
Now, actually, this thing follow is not for the Riemann zeta function. Actually, in general, anything in the LP class, logger polya class,
yes,
as long as the logger polya class, this result just follow. So if you take the shift n to be infinity, then the zeros behave like a zeros of the cosine function.
oh,
But a given polynomial, I don't know the answer. Probably there is no answer, but I don't know. But as you take n tend to infinity, the roots are equal spacing.
oh, so the result is effective. I mean, in the sense,
Effectiveness is a proof. It was a conjecture by Polya, and it was
Okay.
proved by Sordas.
okay, I see.
Yeah, I think the paper came in annals. I think.
Okay, okay, yeah. Okay, thank you.
A good question.
Thanks, Mithun. Any other question?
So I wanted to ask, are there any studies or other Q analogs of these Jensen polynomials which are studied too?
Sorry, go to work.
I mean, is there any Q analogs of Jensen polynomials which are also useful? You take a partition function and put some Q's there.
So-
Okay,
sorry, what do you mean by Q analogs here?
I mean, if Q is 1, then it reduces to Jensen polynomial.
Sorry, hang on. Yeah, one more time. Sorry, I think the voice is breaking a little bit.
If Q is 1, then it should drop down to Jensen.
I don't know. Anyone probably from the audience?
No, but it could be interesting to see,
Yeah, I think that's
especially with the connection with partition function.
Mhm.
You might put some extra powers of Q and just play around and see what happens.
Right. I mean, numerical one can check and then
And just to see what's going on.
right.
Anyway, thanks a lot. Nice talk.
So, Arindam, I had a couple of questions.
Sure.
So one of them was the lower bound on n, starting from which you have hyperbolicity.
Yes.
Does that depend on the asymptotic of the function you are considering? That is, say you are considering
Yes,
P of-
that's right. So very good question. Exactly, that's the point. Yes. So if you look at the partition function SPTN and P bar n, I mean, what happened? They only need the first term, and the first term, although it's a Kuhlsman summation, the first term is everyone can compute, right? And that's the help them to get the So think about that. The constant you are getting in the partition function, they're somehow embedded in the computation when you're computing the lower bound, right?
Yeah.
But somehow you manage to compute if you only using the one term, so you know the constant. That's why getting the n greater than 25 and so on.
Yeah.
Actually, in practice, what they're getting n bigger than, let's say, 200 or 2 million. But then as long as you know the number from 0 to 2 million, you can just do a computer check.
Yeah. The reason I was asking was because if you look at P of n and SPT of n, the lower bounds are higher as compared to when you have P bar of n.
Yes, I was surprised too.
Because there are a lot more over partitions than there are partitions. So,
right. But I think the asymptotic was much more fine-tuned.
Yes.
I think much more like what I'm
Yeah.
telling you, the decay in the second term was so better that allowed to do them.
Okay.
Yeah, but
And
that was
also-
really surprising to get rating n greater or equal to 2.
Right, exactly. And
Yeah.
because when you showed the power partitions, there are fewer than, of course, the number of partitions or the
Yes,
number of
yes.
over partitions. So the number becomes 15,700 or so,
Yes,
like
exactly.
higher.
Yeah. So,
So
it
it
makes
has to
sense to
depend on
there,
the,
but all of a sudden over partition is.
yeah, exactly.
So,
So
that was really surprising, and I think it will also like interesting to look for any other partition. I mean, there are one I mentioned K regular partition, but I know you did some work with Dan and George Andrews and Ajay, and looking all those partitions, and I think that
yeah,
would be really interesting to keep studying, looking those things actually.
yeah. And my second question was that Polya conjecture, where he shows that Riemann hypothesis is defined only if the hyperbolicity.
Right.
There, does that make use of the fact that the Riemann hypothesis is also equivalent to all of the zeros of cap C function being real? The capital
That's
C.
true, because exactly. So you see that like if you put the cap C, and that means xz half plus it, right?
Yes.
So
Yes.
this is the actual real entire function.
Yes.
So that's why you look it's that Taylor expansion, and then basically then you look the Ensign polynomial. Ensign polynomial basically just the cutoff of the Taylor expansion, right, with the binomial coefficient, and you just looking the hyperbolicity of that.
Okay. Okay.
So yeah, exactly what you said, that it is they're looking that one. So it's basically they're looking the real entire function that turn out to be that is the instead of the XZS, they're looking that big theta function. That actually, and it is just a real entire function. So so their Polya conjecture was not focused, is a big setup. If it turn out to be Riemann zeta function is one of the case.
Right. And I think Professor Ajit Iqbal Singh also has another question. She's asking, if not hyperbolic, then zeros in specific sets.
So if not hyperbolic, then zeros in specific set.
There is famous paper by Borsche and Brandon in Annals Maths 2009 or so.
Right. Yeah.
Which specifies conditions, and he gives an introduction Polya-Schur theorem.
Right, that's a good question. Yeah, I thank you. Actually, yeah, that could be another question. If it's not a hyperbolic, then whether it is a
because many leftover cases are there, thousands of them. So
right.
For them, can you put the zeros in a specified set? And Borsche and Brandon do that.
And they did for like almost like all the function, or some like also they have been some.
No. Yeah, they take a sequence, infinite sequence like you did, and then they apply on polynomials like a multiplier, and then they see whether under that transformation zeros are preserved or not.
Okay.
So you are multiplying by your partition number.
Yes,
they multiply by any given sequence. So you can check for your partition number sequence the conditions given by them.
I see. Okay, I'll take a look. I didn't know that paper. Yeah, I'll take a look at that.
Yes, and also I sent to Gaurav my talk at Memphis and a paper which gives applications to quantum entanglement of the binomial theorem. And for binomial theorem, you replace x raised to j by pjx, and you place x raised to n, y raised to n minus j by pn minus jx. You can even take first p from one class and second p from another class, and you have many polynomial classes depending on your n. So you can choose from different ones and have a mixed binomial. And for Laguerre class, there is a mixed binomial, and I had sent my new talk to Gaurav, and I had asked him to display page 45 for everybody. But if he is not able to do so, I can send my talk to you and my papers to you.
Thank you. Yeah, it would be great. Yes.
It is all with Gaurav for the time being.
Yeah, I'll forward it to you.
Okay, good. Thank you. Yeah. Thank you. And they have good applications to quantum entanglement.
Thank you, Professor Ajit. Any other questions? If not, let's